In this video, we present the last of our three techniques that can be applied to solve the solids of revolution problem, right? And so far, we've looked at the disk method, both in terms of X and Y. We've looked at the washer method, also in terms of X and Y. And now the third method, before I tell you what it's called, let me sort of describe the problem to you. And you might think, well, why do we need a third method? Well, there are some instances where the disk or washer approach it fails because of either the algebra that you need in order to set it up, or the after it's set up, if you can set it up, then the integral might be really difficult, right? So here's this problem, right? And again, we're going to have a region that's going to be defined by some curve and the x-axis. So let's say it's something like this. So there's my y equals f of x. And I've only sketched it from x equals a to x equals b, right? Now, if we were revolving around the x-axis, so again, in terms of the region, it's all of this, right? Now, if we're revolving around the x-axis, then no problem. We use our disk method. We would have to take pi times the function squared and integrate it from x equals a to x equals b. But suppose now we're taking this region and we're revolving it not around the x, but around the y, right? So in that sense, when you kind of look at it, it's like, okay, how would I set this up? So assuming we could write this in the form x equals, say, w of y, then how do we figure out the limits? How do we figure out the limits when only, in fact, let me make it very clear, because what I've drawn might be misleading, right? Just so that I'm making it clear, let me take off that part, right? And that part, right? So the region is there, right? So then, if you kind of look at it, there is no boundary here in terms of, if you were trying to think of, like left or right function minus left function, if we were to somehow try to convert this over to a problem in terms of y, it'd be very difficult. Not only that, but maybe the algebra that's needed to solve for x in this situation might be very, very difficult. So let's think through an alternative approach to solving this particular problem. Now, one of the reasons why I did the shading this way is that I would say, well, suppose I just took one of these intervals. So let's say we do have a partition, like we did in our Riemann sum several times now. So let's say we have a partition. Let's call this small width delta x. And then what I'm going to do is, from this interval, again, pick a special value. So pick a special x. And again, I'll label it over on the side when we have a little bit more room. But let's say this is my x. Find the height at that point. And then essentially, when we revolve this around the y-axis, what we're going to end up is something that looks, it's going to go all the way around, and then I'm going to revolve this part too all the way around. So it's going to go all the way around like here, and then all the way around like here. It is going to be hollow in the middle, right? And then, of course, there is going to be some height to it because it's going down to the x-axis, right? So just one of these things, right? It's like this. It's almost like a hollowed out shell, right? And it's going all the way around the y-axis, right? So we have the delta x there. that represents the thickness of the shell, right? That's one thing. We have, so right where I have the little red mark going across to the y-axis, right? That's the height, right? So this distance right here is the height, and that is determined by, again, your f of x and which x value I've chosen, right? And then the third piece of this is there's a radius. There's a radius of this because this is a circular like cylinder going all the way around. But again, the middle part is cut out, so it's almost like a shell, a cylindrical shell. And then we have a radius that goes from the axis to that outer, or actually to the value of x that I've chosen right here, right? So it's a little misleading, but let me write down everything, right? In fact, what I will do is, let me use a different color, and this distance right here from the x value that I've chosen to the middle, which is the axis of revolution, this will be the radius. So let me write everything on here. So the green distance there is the radius. Well, what is that distance? Well, that depends on whatever x I choose. If I choose my x down here, then the radius will be that x value. If I choose my x value to be here, then the radius will be right there. So the radius is whatever special x value I choose, right? This right here that I already have labeled the delta x, that's going to be my thickness, how thick it is, and that depends on my delta. So the smaller my delta, the thinner this shell is, right? So this is the thickness, and then the red, that's the height. And over here I'll write down what the formula is. So now this is how tall the shell is. So again, if I choose my x out here, the shell would be this height. If I choose my x right here, the shell would be this height. So whatever the value of the function is at the x value that I've chosen, this special x right here, that's going to determine the height of the shell. And then the formula or the expression for it will be my function value at whatever special value I pick. So for instance, if I'm doing a Riemann sum and I end up picking the right endpoint, which would be like this, then the height would be right here. Then it would go all the way around because the revolution is now with respect to the y-axis, right? So we have these three key components. And the question is now, so let me, again, this is hard to see. So I want to find the volume of this cylindrical shell, right? So the question is, what is its volume, right? So think about it. What is the volume? So what is the volume of this cylindrical shell? Well, the thing about the cylindrical shell is that if we could figure out a couple things, so like if we could figure out the distance all the way around the shell, right? So all the way around, and then multiply it by its height and the thickness, that would give me the volume, right? So think about it. So if I knew the distance all the way around, which is kind of this, well, actually, let me say it this way. Yeah, so if we knew the distance all the way around, multiply by its height, the height as well as the thickness of the shell, that would give me its volume, right? So we need to figure out what is the distance that's going all the way around. Well, the cross section here of the shell is circular. It's a circle. And I know its radius, right? So the distance all the way around the shell is the circumference of a circle of radius this value, right? So let's write that down. So the circumference of the shell, which is again the distance going all the way around. So the circumference of this one shell is, it's 2 pi r, but what's the radius? It's this x value. It's that distance right here. That's the radius, and then we want to know the distance all the way around. So that's 2 pi, not r. I'll write the x bar k, right? And then if I multiply that by the height, right, that will give me the volume. Right? So if I multiply this quantity times the height of the shell, right? So basically, like when you do this, again, you're getting the circumference all the way around, and then that's the distance. And then if I take the height and multiply that distance all the way around, that's like the area. And then when I multiply by the thickness, that gives me the entire volume of this, right? So if I take the circumference, so let's write this over here. If I take the circumference, right, times the height, that gives me the cross-sectional area. And then if I multiply by the thickness of the shell, that gives me the volume. So times the thickness, right? But that's just for one of them. That's just for one of these shells. I would have to repeat that process for every sub-interval, and every time I choose a different x, I would have a different height and a different radius and a different circumference as a result of that. So then I'd have to add them all together. So this tells me now the volume is approximately equal to, and it looks like another Riemann sum. So now my k will go from 1 to n. And again, take the circumference, which is your 2 pi x bar k, times the height, which is your f of x bar k, and then how thick this shell is, right? Even though it's hollowed out, there's some thickness to it, but you have this outer region and then this inner region, and then so the thickness there, well, that's my delta x, right? So then, as with every Riemann sum, two ways I could say it, right? If n gets very, very large, or delta gets very, very small, as long as our function behaves nicely, and for us, all our functions are going to behave nicely because we're going to assume continuity. But these Riemann sums all get closer and closer to the actual volume. So how do we get it precisely? Well, we take the limit as, let's say, delta x goes to 0. So our volume is going to be exactly the limit as delta x approaches 0 of our Riemann sums. Right? So we have our 2 pi x bar k times f of x bar k times delta x. And again, the region here starts from x equals a, goes to x equals b. So then what we know happens is that this limit of a Riemann sum converges to our definite integral. So it's the integral from a to b, and then all the x bars just change to x, and therefore the f of x bar changes to f of x, and the delta x changes to dx. So it's the integral from a to b of 2 pi x times f of x dx. And let me write a v there. And this is the famous, or maybe infamous, volume by cylindrical shell formula, right? So this is our volume by shells, right? And again, just to recap, the thing that's different about this is even though my function is in terms of x and the limits are on the x-axis, the shell formula now gives me the volume of the solid formed if I revolve around the y. So previously, using the disk method and the washer method, if we had to revolve around the y, we had to convert the equation in the form x equals a function of y, and we had to find the limits on the y-axis. The shell method doesn't require us to do that. It means we can take our function, which might just be given in terms of x, and our limits are on the x-axis, but if the revolution is about the y-axis, the shell method in many instances give us an alternative approach where the algebra might not be as difficult, right? Right, so there are a couple variations of this, right? And the first one is, okay, so what if we have two functions, right? So let me describe the first variation of this. So what if we have two functions in terms of x, so an upper function and a lower function. And the region, so, is still defined by limits on the x-axis. But now let's say the revolution is about the y. And again, both of these equations might be difficult to solve for, right? In terms of if we wanted to try to set it up in terms of y. But with the shell method now, what we can do is kind of modify our approach. Well, what needs to modify? Well, the big difference is this region doesn't go all the way down to the x-axis. So the height is not from f down to the x-axis, but the height is now from f down to g. Well, what is that height? Well, if you pick a specific x value, the height would just be your upper y minus your lower y. And that's it. So you basically take a difference and that becomes your height, right? So let me write it up again. It's sort of piecewise so you can see it. The radius is still going to be x because you'll choose like a x bar here, and then the radius is the distance from the x value to the axis of revolution. The axis is always going to be the middle, kind of the middle of your solid. And then the radius will be, in this case, from your axis of revolution up to whatever you choose. So your radius is still going to be x. That means your circumference is still 2 pi x, because again, going all the way around, right? So your circumference is 2 pi x. The height is now what changes. The height is the difference between the upper function f and the lower function g. And then your thickness is still the delta x, which is going to become your dx. So I'll just write it like this. The thickness is your dx, which is really, really small. In fact, it's infinitesimally small. So when you put all these pieces together, now if I take a region like this and revolve it around the y-axis, here is the formula. The limits, still a to b, we still have the circumference, and now the difference is the height is f of x minus g of x. and then times the thickness dx, right? So this is still considered a shell formula, and I think, again, let me reiterate, what sets the shell apart is that you're allowed to have your function in terms of x, your limits are allowed to be on the x-axis, but then you're revolving around the y-axis, right? So that's one variation. Now the other variations are saying you can do the exact same thing, but flip it around. Have your function in terms of y, your limits on the y, but then revolve around the x, right? So I don't just want to say it, but let's actually go through and draw it so you can see what that variation looks like. Right? So now you could have something that looks like this. So then let's say this is your x of wy, but just one function. And then the region is from here up to here. So it's now, again, I'll do these horizontally. And as usual, on the y-axis, we're going to use c and d, right? So the limits are on the y. The function is in terms of y, but let's say we revolve around the x-axis, and we don't want to go through the algebra of having to convert everything over to x and use something like a disk or a washer. So we can have a problem that's set up like this, and then the volume, in this case, of the solid that's formed when we revolve around the x-axis will be given by this integral. So it's the integral from c to d. You'll have 2 pi, but now it's going to be y, and then your height in this case is this horizontal distance from your axis to how far out the curve is. So then that's your w of y, and then dy, right? And then lastly, the last and very last variation is, what if you have two functions in terms of y and then the region is stuck between them and you have the limits on the y, but again you're revolving around the x-axis. So finally, so if you have something like this, let's say we have a curve like that, so let's call this one x equals w of y, and let's call this x equals v of y. And again, the region starts at y equals c and goes to y equals d. But now it doesn't go all the way down to the y-axis. So it starts from your function on the right to your function on the left. And as you might guess, we're not revolving around the y, we're revolving around the x-axis. And then what happens now is, again, we take the same approach. Our volume in this instance is the definite integral from c to d. It's going to be 2 pi y. But now we have to take the difference. So the height of the shell, right? Because now remember that. So right now it's going to go around the x-axis like that. But the height of the shell is the difference between the larger x function and the smaller one. So we have the quantity wy, or w of y, minus v of y, and then that integral is with respect to y, right? So if you list all the different cases going back to the disk, so going back to the disk, we had two, one in terms of x, one in terms of y. Then to the washer, we ended up having another two. So again, a washer in terms of x and a washer in terms of y. So that brings us up to 4. Now if we include these 4 possibilities with the shell method, we have a total of 8 different approaches, right? And some of them are equivalent depending on how much algebra you do in terms of your conversions, right? You might end up with an integral that's a lot harder to do, but then a different approach might present itself with an easier integral to work with, right? And how do you know? You really don't know. There's no general approach to say always use this or always use that, but it's taking each problem and looking at it case by case. So let's do an example of this, right? So let's look at an example. So what I will do here is sketch the function. So let's say our function is, well, one function is this. It's going to be a constant. So we have y equals 2. And then we have, let's say, y equals x squared, right? And let's say here's our region between these two, right? And we're going to revolve this about the y-axis, right? So about the y, this is our axis of revolution, and the question is, what is the volume formed, right? So what is the volume of the solid that's formed? All right. Well, if we kind of look at it, so we can see that the function, now this one's a constant, but we can see it's in the form y equals. So if we could figure out what this limit is, right? We can see that this one starts at x equals 0. If we can figure out what point of intersection this x value corresponds to, then we can go ahead and use our shell method, right? So let's figure out what that point of intersection is. So let's take our x squared and set it equal to 2. Well, technically speaking, x would be plus or minus root 2. But because the region here is in the first quadrant, the x has to be positive. So x is equal to root 2, and this is because the region is in the first quadrant. So the negative root 2 is not valid for the given problem, right? Okay, so then let's write down the integral that gives us the volume using the shell method. So again, I'm not going to use any algebra. You could set this up in terms of y fairly easily, but I wanted to demonstrate how we can use the shell method. So using the shell method, let's write down what it is. So v equals the integral, and we'll go from 0 to the square root of 2. And it's going to be 2 pi x. So we have this extra x now. And then we have to take the larger function, because now the region doesn't go all the way down to the x-axis. So we have to take the difference between the larger function and the lower function. So the larger function here, because the constant y equals 2 is on top, the larger function is a constant 2, and then the lower function is our parabola, the y equals x squared, so minus x squared. So this is the setup, right? And this setup, it will give us the volume, and notice we didn't have to, the only algebra we had to do is to figure out that point of intersection so that we can know what the upper limit is, right? Well, let's go ahead and evaluate. So the 2 pi, that constant multiple we can take out of the definite integral. And then we go from 0 to the square root of 2. And then let's distribute the x. So we will have 2x minus x cubed dx, and then I can use my power rule. So let's see what we have. So we got the 2 pi, and then when we take our antiderivative, we'll end up with x squared minus 1/4 x to the 4th, and then this goes from 0 to the square root of 2. So we have 2 pi. Now let's plug in the upper limit. So when I plug the square root of 2 here and I square it, the root goes away. So I have 2 and then minus, and then I'll have 1/4. Now when you take the square root of 2 to the 4th power, that's the same as 2 squared. Why is that? Well, if you have the square root of 2 to the 4th power, that's 2 to the 1/2 to the 4th power, and our property of exponents says I multiply these powers. So this is 2 squared, and 2 squared is 4, so I'll put that there. And then what's nice about this is at the lower limit, both terms are 0, right? So look at what we have. We have 2 pi times the quantity 2 minus 1, so we end up with exactly 2 pi cubic units of volume, right? So with the shell, it gives us an alternative approach. If we, for instance, sometimes you might just want to keep the functions in terms of x, but if the question is saying that the axis of revolution is now the y-axis, well, if you want to keep the functions in terms of x, then you'd have to use the shell method, because what it basically does, it gives us the opportunity to get the volume of a solid that's formed by revolving around the y-axis, even though the function and the limits, the integrand and the limits of integration are in terms of x, right? So it's a different setup as opposed to the disk and the washer methods where everything was in terms of the same variable. The function in terms of x, the limits in terms of x, and the revolution was about the x-axis, right? And that's the difference between the three, right? See you in the next video.